Welcome to week 11 of problem solving sessions for the digital electronic circuits course. This week we'll be looking at analog to digital converters and digital to analog converters. As usual, we'll be covering uh, topics that were taught in week 11, and there will be 10 problems. Here is question 1. For a 3-bit weighted resistor DAC circuit shown below, what can be the values of R0, R1, R2 and RL respectively? This 3-bit weighted resistor DAC circuit was covered in lecture 51. You can refer to slide number 5, and there you see that R1 must be half of R0, R2 must be R0 by 2 square, which is R0 by 4, and RL must be much greater than R0 for this particular DAC circuit. And if there are more than 3 bits, I think it will go as powers of 2. So R1 is R0 by 2, R2 will be R0 by 4. If there's R3, it will be R0 by 8. There's R4, it will be R0 by 16, and so on. That's all you need. And next you see which option follows this pattern. So there's no one particular value of resistance that you need to give. If you choose R0 differently, then R1, R2 will be different. And RL also you can choose in different ways. RL much greater than R0 doesn't give you an exact value for RL. And when you look at this, Let's see, here you have 25 kilo ohm, that's your R0. Actually, the order they have given is R0, R1, R2. So the first resistance is R0, 100 kilo ohm. Then R1 must be R0 by 2, should be 50 kilo ohm. And R2 is R0 by 4, which is 25 kilo ohm. The RL must be much greater than R0. Mega ohm is 1000 kilo ohm, so it's 10 times R0. So RL is much greater than R0. And from that you can conclude that the answer is option B. If they have given more resistors, more bits in the DAC, and like I said, you just the resistor connected to the LSB is the highest value, and then every next resistor will have its value divided by half. That's question 1. We'll go to question 2. Let me get the question on the screen. In the below R2R ladder DAC circuit, RF is R and V reference is 10 volts. If the analog output VA is 9.37 volts, what is the binary input at V3 MSB2 V0 LSB of the digital to analog converter? So first V0 to V3, which is a binary number that you give, binary input, is converted to its gray code form, and that is fed to a digital to analog converter. Now here a little bit of guesswork has to be done. Here there are 4-bit digital to analog converter, and it's an R2R ladder network. Let's see. This was also covered in lecture 51. In the R2R ladder network, the output voltage VA is v3 by 2 plus v2, or if we start out from v0, you can write this as v0 by 16 plus v1 by 8 plus v2 by 4 plus v3 by 2, or you could write this as into vref, or you could take the 16 out and write this simply as v0 plus 2v1 plus 4v2 plus 8v3 and a little bit of guesswork has to be done. VRF is 10, so it's 10 by 16. So to get 9.37, you need 1111. So the input 1111 will be given as, in digital it's 1111, so the analog voltage will be 9.37 volts. And now the binary input which gets converted to 1111 through the gray counter is 1010. If you put it to a gray counter, if you convert it into a gray number, it will be 1111. So the actual input that you should give is 1010. That will be converted by the gray counter to 1111, and that will be converted by the digital to analog converter to 9.37 volts. Alright, we'll go to question 2. Question 3. Question 1, the slide we are referring to is this. I'll just leave that there as reference. You can see that you have R0 as your resistor connected closest to the MSB, resistor connected to the MSB, R0 by 2 as the resistor connected to the next bit. Sorry, R0 is connected to the LSB, R0 by 2 is connected to the next bit, R0 by 4 to the next bit, and so on. If you have more bits, then you'll have R0 by 8, R0 by 16, etc. So that's reference for solving the first question. That slide is the reference to solve question 2. VA is V0 into 2 power 0 plus V1 into 2 power 1 plus V2 into 2 square, etc. up to Vn minus 1 2 power n minus 1, the entire thing divided by 2 power n. And the answer was option A, 1010. Okay, we'll move on to question 3. The below circuit Rref is 10 kilo ohm and Vref is 10 volts. R is 5 kilo ohm. Find the value of V0 if the input is 1 0 0 0 0 0 0 1. First thing, this IC DAC 0808 is an 8-bit DAC IC, and the output voltage is Vref by Rref into A1 by 2 plus A2 by 4 plus etc. plus A8 by 256 into R. Substituting the values that they have given, Vref is 10, Rf is 10 kilo ohms, and R is 5 kilo ohms. This is 10 by 10 into this into 5. And A1 is 1, A8 is 1, rest are all 0. So you get half plus 0 by 4 plus etc. plus 1 over 256, which will be 0.503. Half is 0.5 and 1 over 256 is 0.003 something. Into 5, which is 2.51 volts. So the answer is option D. In all these questions, what you need to remember is which circuit, what type of circuit it is. Is it a digital to analog converter, or is it a analog to digital converter? And then once you know which type of circuit it is, among those, further which exact or which specific circuit configuration does it have. So is it a weighted binary weighted resistor DAC, or is it an R2R ladder DAC? What type of configuration does it have? And based on that, the output voltage will be some combination of weighted weighted combination of voltages where the weights are given by the input bits. What I mean to say is, so the first bit A1 is weighted by Vref by Rf into R into half. Second bit is weighted by Vref by Rf into R by a quarter, and the MSB LSB A8 is weighted by Vref by Rf into R into 1 over 256, which is 2 power 8. So the weights here are powers of half, or you could say they're divided by 2 power some number, and that number depends on which position the bit is in. So the LSB is weighted by 2 power 1, second bit is weighted by 2 power 2, the nth bit is weighted by 2 power n. It's a similar situation in binary weighted resistor DAC also. In this particular circuit that they have given, you would have your VA, the output would be 1 over 7 into, so here instead of 1 over, in your ladder circuit you have 1 over 2 power n. So n is 4 in this question, so you have 1 over 2 power 4, which is 16. In this weighted resistor circuit, instead of 1 over 2 power n, you have 1 over 2 power n minus 1. So it's 1 over 7 for this particular circuit into V0 plus 2V1 plus 4V2. So again you have powers of 2 as multipliers, and the MSB has 2 power 0 sorry, the LSB has weight 2 power 0. So it's V0, and the next bit has 2 power 1 as its weight. It's 2. Next bit has 2 square as its weight, 4. So how these bits are weighted will differ slightly based on the type of circuit you have, and there will be a similar situation for analog to digital converters. We'll go to question 4. A 16-bit DAC is calibrated over the full range from 0 to 8 volts. The input to the DAC is DEC in hexadecimal. The output is how many volts? And the solution for this question is resolution of the circuit would be VFS, full scale voltage. So here it is 8 volts divided by 2 power n minus 1, where n is the number of bits. N is 16, VFS is 8, so resolution is 8 over 2 power 16 minus 1. That is, you have 0, the number with all zeros is represented by 0 volts, so you don't need any output voltage for that combination. Other than 0, there are 2 power 16 minus 1 possible binary numbers which are of 16 bits. So each bit can either be a 1 or a 0. So there are 2 power 16 numbers in total including 0. If you remove 0, there are 2 power 16 minus 1. And each of those must be given a different, must give a different voltage value within 0 to 8 volts. So the full range of voltage that you have from 0 to 8 must be split such that split into 2 power 16 minus 1 parts, so that you can distinguish between two different numbers by measuring the voltage. So each 16-bit input will give you a different voltage within the range of 0 to 8 volts. And if we divide it equally, the entire range 0 to 8 volts, if we divide it into equal parts, then every the difference in voltage between every number will be the same, which will be the resolution, which is 8 over 2 power 16 minus 1 in this case. Now the input number Vn is DEC in hexadecimal, just 3564 in decimal. So for a 16-bit DAC, the output voltage can be written as the resolution into the decimal equivalent input, which is 8 over 2 power 16 minus 1 into 3564, just 0.435 volts. So the answer is option C. Question 5. For a flash ADC circuit, which among the following figures denote the relationship between the number of bits in digital output and the number of comparators required? There are three figures. In the first figure, the number of comparators is increasing exponentially with the number of bits in the ADC output. In the second figure, the number of comparators is increasing linearly with the number of bits in the ADC output. In the third figure, the number of comparators is the same regardless of the number of bits in the ADC output. They're asking which of the figures accurately represents what happens in a flash ADC circuit. That what I have given is the circuit for a is an example of a flash converter. You can see the number of comparators there. For 3-bit analog to digital converter, you need 7 comparators. because you divide the entire voltage range into 2 power n minus 1 different levels, including the level with 0 volts, that would be 2 power n voltage levels. So an n bit ADC for this type of flash converter, you can see clearly it requires 2 power n minus 1 comparators. 2 power n is exponential in n, so if n is the independent variable, then the number of comparators 2 power n minus 1 is an exponential function of n. So the correct representation is given by figure 1. Alright, we are halfway through. I'll take a small break and come back. Okay, let's see question 6. Question 6. For a 3-bit flash converter ADC shown below, what will be the encoding logic for MSB bit denoted as 2 squares? So what is the encoding logic for MSB in terms of comparator output? So we saw this flash converter circuit here. And you can see here for this 2 square is just C4. But that, so from that you can directly say that it is option C. But let's go ahead and look at why, how we got that. So we'll write a truth table to find the encoding logic. So input voltage, and based on that input voltage, which of the comparators give a high output, and based on the comparator values, what will the encoder output be. So the input voltage has several different ranges from 0 to VO rate. Only none of the comparators give you a high output. They're all 0, and all zeros will be encoded as 000. From VO rate to VO4, the comparator 1 will give you output 1, which will be encoded as 001. from V/4 to 3 V/8 volts. Both C2 and C1 are high, so this is encoded into 010 for 3 V/8 to V/2. C1, C2, C3 all give you a high output, and that is encoded as 011. For V/2 to 5 V/8, 5 V/8 to 3 V/4, 3 V/4 to 7 V/8, 7 V/8 to V. For V/2 to 5 V/8, 4 of them are on, that is encoded to 4100. For voltage values 5V/8 to 3V/4, first 5 comparators are on, so that's encoded as 101, and so on, 110. And from this truth table you can see that the MSB2 square is 1 for the last 4 voltage ranges, so from V/2 to V, and in that case the comparator C4 gives a high output in all those 4 cases, and it's a low output for all the other cases. So whenever C4 is 1, your MSB2 square is also 1. That's why MSB bit is high only when C4 is also high. And if you write out the truth table for the other bits, you will from the truth table you can find the logic for the other bits, and you'll find that 2 power 1 is 1 in these 4 combinations, and in those 4 combinations either C6 is high or C4 is low and C2 is high. So the encoding logic is C6 plus C4 complement C2. Similarly for 2 power 0, the encoding logic is C7 or C6 complement C5 or C4 complement C3 or C2 complement C1. And this encoding logic is actually here, it's a priority encoder that we are using, not a normal encoder. IC9318 can be used for this. It's very simple, and fast, so we call it a flash converter, but the number of comparators increases exponentially with n. So if you have too many bits, it's not, you need a very large circuitry, so it's not that good. Question 7, for an ADC match the following. If this one, continuous conversion, 2 is dual slope, 3 is delta sigma conversion, 4 is successive approximation. List 2 gives what kind of circuit you have and other conditions. Uh, One is requires a weighted resistor network. 2, conversion time linearly proportional to number of bits. 3, robust against noise interferences. 4, does not help in processing time for multiplexed input. 5, high resolution but low processing speed. And the so here is the solution. Continuous conversion needs to restart from the beginning for multiple analog inputs processed via multiplexing. Hence, under such situations, processing time needed becomes large as tracking is not possible. That's about continuous conversion. Next, due to integrating dual slope conversion averages out noisy interferences originated mainly due to power supply fluctuations. That's about dual slope. Next, delta sigma conversion requires the analog output to be oversampled. so it can convert smaller amplitude variations. However, due to more numbers of complex components, the processing time is more. Next, about successive approximation. Requires n iterations in clock cycles to convert an analog signal using n bit digital equivalent. So using these four things you can match list 1 to list 2, and the answer turns out to be option D. Q8. An 8-bit successive approximation register type ADC is used to convert 4.75 volts to digital output. The reference voltage is 12 volts. The output of ADC at end of third clock pulse after the start of conversion is here resolution is 12 over 2 power 8 minus 1, which is equal to 0.0547 volts. The digital output at 0th clock pulse is 0.00000000. Then at first clock pulse, the digital output will be 10000000, corresponding analog voltage VDAC is 0.047 into 128, decimal of 1,000,000,000,000. So this is 6.02 volts, which is greater than 4.75 volts. So digital output at the second clock pulse will be 01000000, which will give you 3.0117 volts, which is less than 0.75 volts. Then third clock pulse 01100000, output will be 4.5176 volts. So the answer is option B. Question 9. A 16-bit counter type ADC is operating with a 3.60 GHz processor. What is the average processing time for the conversion? Maximum conversion time for a n-bit counter type Maximum conversion time for an n-bit counter type ADC is 2 power n clock pulses. So the maximum time period is 2 power 16 clock pulses, and each clock pulse, the clock frequency is 3.60 GHz, so the time period of one of the clock signal is 1 over f, 1 over 3.60 into 10 power 9. So that maximum conversion time is 2 power 16 divided by 3.6 into 10 power 9 seconds, which will be 18.20 microseconds. And the analog input can lie anywhere between the min and max voltage range with uniform probability. So the average conversion time equals Tmax by 2, so it is 9.10 microseconds. So the answer is option A. Question 10. In a single ramp type ADC, given R is equal to 2 kilo ohm and C is 0.5 nanofarad, and we input is 3.5 millivolts for the ramp generator circuit. Consider the clock frequency to be 1 megahertz. If the ADC generates the digital output after 512 clock cycles, find the ramp voltage. Slope of the ramp is Vi by Rc, which is 3.5 millivolt by 2 into 10 power 3 into 0.5 into 10 power minus 9, which is 3.5 millivolt per microsecond. Clock frequency is 1 megahertz, so 1 clock pulse so the clock period is 1 microsecond. So after every 1 clock pulse, 1 time period will have passed, so the voltage will increase by 3.5 millivolts. So 1 clock pulse increases ramp voltage by 3.5 millivolts. So after 512 clock pulses, ramp voltage equals 512 into 3.5, which is 1.79 volts. So the answer is option D. I will wait here for 8 more minutes till 5:30 p.m. If any student joins, they can clear their doubts, or else I'll leave at 5:30 p.m. If you are watching this on YouTube, thank you for watching. If you have any questions regarding the problems, you can ask them in the next live session, which is next Saturday.